Welcome to our presentation on Exploratory Data Analysis in SPSS. This is a step-by-step guide specifically tailored for economic and research data. Throughout this session, our primary goal is to equip you with the skills to effectively diagnose your data. By thoroughly exploring your dataset, you can uncover meaningful insights and, critically, ensure that the statistical techniques you choose are appropriate and robust for your research. Think of it like this. Before you build a house, you meticulously survey the land. EDA is that essential survey for your data, ensuring a solid foundation for any complex statistical model. We'll examine why this initial data exploration is so vital in economics as we delve into avoiding the garbage in, garbage out dilemma.
In economic modeling, we often take raw data, such as income distribution, and feed it directly into a predictive model to forecast outcomes like household debt. If we treat this model as a black box and overlook the quality and characteristics of our input data, we run a significant risk. The outcome is often flawed policy recommendations, embodying the classic problem of garbage in, garbage out. For example, if our income data includes a few super-rich individuals, these outliers can drastically skew the average income. A policy built on this distorted average would then be entirely invalid for the majority of the population. This is precisely why exploratory data analysis, or EDA, is not optional. It acts as our crucial safety check, allowing us to move from mere guesswork to informed, evidence-based decision-making, ensuring our models produce reliable and actionable insights. EDA is truly the solution to preventing erroneous policy.
This slide presents our statistical decision map, a guiding flowchart for selecting the appropriate analytical method. We begin by identifying our variable type. Is it categorical, like gender, or a metric or scale variable, such as income? For categorical data, the path is straightforward. We typically use frequencies or crosstabs to understand counts and proportions within our groups. However, for metric or scale variables, we enter a crucial diagnostic phase, where the Explore procedure in SPSS becomes our primary tool. The Explore procedure is vital because it helps us answer a critical question. Is our data normally distributed? The answer dictates our next step. If the distribution is normal, we can proceed with powerful parametric tests like t-tests and ANOVA. If not, we must opt for non-parametric alternatives. The Explore procedure effectively bridges the gap between our raw data and our choice of hypothesis testing, ensuring we apply the correct statistical approach. This procedure is especially useful when examining a scale variable across different groups defined by a categorical variable. After understanding the importance of data screening, let's look at the specific tools SPSS provides and when to use each. The frequencies command is your go-to for categorical data, offering simple counts and percentages to understand the distribution of non-numeric variables. For scale data, if you need overall summaries, z-scores, or basic descriptive statistics for your entire sample, the descriptives command is appropriate. However, when you need to delve deeper and perform crucial diagnostic checks, the Explore command is the heavy lifter. Unlike descriptives, Explore is designed for a more comprehensive data audit, especially when comparing a scale variable across different groups. It's unique in providing both visual diagnostics, such as boxplots, and robust normality tests, like the Shapiro-Wilk test, all in a single, efficient procedure. This capability is vital for identifying outliers and confirming distributional assumptions before proceeding with more advanced statistical tests. Now, let's delve into the mathematical foundations of some of the key statistics that the Explore function provides. To effectively explore our data, it's vital to understand a few foundational statistical measures. First, the 5% trimmed mean is a robust measure of central tendency. It's calculated by removing the top and bottom 5% of observations, then computing the mean of the remaining data. This helps us gauge the influence of extreme values. For example, if your regular mean income is $50,000, but the 5% trimmed mean is $45,000, that significant difference strongly suggests influential outliers are pulling the average up. Next, the interquartile range, or IQR, quantifies statistical dispersion. It's simply the range between the third quartile and the first quartile, representing the middle 50% of your data. Lastly, the confidence interval, or CI, provides a range where we can be reasonably confident the true population mean lies. A 95% confidence interval means we are 95% confident that the true mean falls within that specific range. These statistics are crucial because many powerful econometric models rely on a set of strict assumptions about the data. Let's review these critical conditions. Before applying powerful parametric tests, it's crucial to check 4 key assumptions. First, normality. Our data, or specifically the errors in our model, should follow a normal, bell-shaped distribution, which we typically assess using QQ plots and formal tests. Second is homogeneity of variance, also known as homoskedasticity, meaning the spread of data should be consistent across all groups, often checked with Levene's test. Third, independence. Observations must be independent, usually guaranteed by random sampling and good experimental design. And finally, the absence of outliers. Extreme values can significantly distort our model estimates and conclusions. It's vital to remember that most parametric tests, like OLS regression, heavily rely on the normality assumption. If our exploratory data analysis reveals a violation of this check, we must either transform our data or consider using non-parametric statistical methods to ensure the validity of our findings. The normality assumption is particularly important, so let's look more closely at how we interpret the shape of our data's distribution. This slide illustrates how we interpret the shape of our data's distribution, a critical aspect of exploratory data analysis. We primarily look at 2 characteristics, skewness and kurtosis. Skewness measures the asymmetry of the distribution. A positive skew, like what we often see with income data, indicates a longer tail on the right, meaning most values are concentrated on the left. Conversely, a negative skew has a longer left tail. Kurtosis measures the tailedness or peakiness of the distribution. A leptokurtic distribution is tall and thin with heavy tails, often implying more outliers, while a platykurtic distribution is flatter and wider with lighter tails. To formally assess if our skewness or kurtosis values are statistically significant, we can calculate a z-score by dividing the statistic by its standard error. However, for many practical economic analyses, a helpful rule of thumb is that if the skewness value falls between -1 and +1, the data is generally considered sufficiently normal for most parametric tests. Understanding these shapes helps us decide if our data meets the normality assumption required for various statistical models. To begin our data analysis in SPSS, we'll navigate through the main menu at the top of your screen. The process is quite simple. First, click on Analyze, then hover over Descriptive Statistics, and from the submenu that appears, select Explore. This Explore command serves as our primary dashboard for any deep data audit. It's the go-to function when you need to comprehensively examine your scale variables, particularly when you're comparing them across different groups. If you've just loaded your dataset, this is often the very first practical step to take. Clicking Analyze, Descriptive Statistics, Explore will open the main dialog box, which is where we'll set up our entire diagnostic check. Once this dialog box is open, we can proceed to configure our analysis, which we'll discuss next. Once we've navigated to the Explore command in SPSS, we'll be greeted by this dialog box, which is our central hub for setting up the analysis. Here, we define the variables we want to examine. In the dependent list, you'll place the metric or scale variables you wish to analyze for diagnostics, such as salary or distance from home. Below that, the factor list is where you'll add any categorical grouping variables, like gender or department, if you want to perform the analysis for different subgroups. A critical pro tip on this slide highlights the Label Cases By box. It's highly recommended to place a unique identifier variable here, such as customer ID or employee ID. This allows SPSS to instantly identify the specific data row of any outlier it detects in your analysis, making investigation much more efficient. After setting up these variables, our next step is to specify which statistics and plots we want SPSS to generate.
Once you've set up your variables, the next step in SPSS's Explore procedure is to configure the specific statistics and plots you want to generate. In the Statistics subdialog, it is crucial to check the Outliers box. This setting is vital because it will produce a specific table highlighting the top and bottom 5 most extreme values in your data, making the identification of potential outliers straightforward and saving significant time compared to manual sorting. Following this, in the Plots subdialog, you must select Normality Plots with Tests. This option instructs SPSS to perform formal statistical tests for normality, such as the Shapiro-Wilk test, and include their results in the output. This two-step setup ensures you gather both numerical data on extreme values and the critical p-values for normality testing. With these options configured, we are now ready to apply these steps to our case study and interpret the resulting output.
Our case study delves into an interesting question within economic geography. Do shopping catchment areas vary by demographic group? Specifically, we're examining whether male and female shoppers travel different distances from their homes to shopping centers. For this, we'll utilize the retail.sav dataset. Our primary objective is to determine if there's a significant difference in the travel distances between these two groups. In our setup, distance serves as our dependent scale variable, while gender is our categorical factor variable. Understanding these patterns is crucial for retail developers. For instance, if one gender consistently travels farther, it might influence where they focus advertising efforts or consider new store locations. Now, let's look at the SPSS output to interpret our findings for this case. The first output table we examine from the Explore procedure is the Descriptives table. Here, our main focus is on comparing the standard mean with the 5% trimmed mean. For the male group in our retail geography case study, we see that the mean distance is 6.0, while the 5% trimmed mean is 5.95. This remarkably minimal difference between these two values is a crucial indicator. It tells us that extreme observations, or outliers, are not significantly influencing the central tendency of the data for this group. Therefore, the simple mean of 6.0 appears to be a robust and reliable summary statistic. If, for instance, the mean had been 6.0, but the trimmed mean was much lower, say 4.5, it would signal that a few individuals with very high distance values were skewing the average, necessitating further investigation into those extreme cases. Having established the central tendency, our next critical step is to validate the assumption of normality. This slide focuses on validating one of the most critical assumptions for many parametric tests: normality. We use the Tests of Normality table from SPSS, specifically looking at the Shapiro-Wilk test results, which is generally preferred for smaller to moderate sample sizes. The null hypothesis, or H0, for these tests is that the data is normally distributed. Our decision rule is straightforward. If the sig value, which is the p-value, is less than 0.05, we reject the null hypothesis, concluding that the data is not normal. Conversely, if the p-value is greater than 0.05, we fail to reject H0, meaning we can assume normality. For our distance variable, we see that for males, the Shapiro-Wilk p-value is 0.043. Since this is less than 0.05, we conclude that the distance data for males is not normally distributed. However, for females, the p-value is 0.421, which is greater than 0.05, indicating their distance data is consistent with a normal distribution. This is a crucial distinction, as the non-normal data for males means we cannot use standard parametric tests, like a t-test, if we were to compare mean distances between genders. Instead, we'd need to consider a non-parametric alternative, such as the Mann-Whitney U-test. Boxplots are incredibly useful visual diagnostic tools, especially when we need to compare distributions across different groups, proving superior to histograms for this purpose. This diagram illustrates the key components of a boxplot. The central box itself represents the interquartile range, encompassing the middle 50% of our data. Inside this box, the prominent line marks the median, which is the exact center of our data's distribution. The lines extending from the box are called whiskers, which show the full range of the data.
excluding any extreme values. Individual dots plotted beyond these whiskers are our statistical outliers. For instance, in our retail geography analysis, the box plot clearly flags cases 101 and 67 as statistical outliers. As a useful diagnostic, pay close attention to squashed boxes. These indicate low variance and high agreement within that particular group, offering quick insights into data spread. Having identified these outliers visually, our next step is to delve into the SPSS output to pinpoint these specific cases and determine the appropriate course of action. After identifying potential outliers through visual diagnostics like box plots, our next step is to examine the extreme values table, which lists the specific cases with the highest and lowest values. For instance, here we see case number 101 for males has a value of 2.0. The crucial rule is never delete outliers mechanically. Instead, you must investigate the cause. There are two primary scenarios to consider. First, the extreme value could be a simple data entry error. Perhaps a distance of 20.0 was mistakenly typed as 2.0. If this is the case, the appropriate action is to either correct the error or, if uncorrectable, delete the entry. Second, and often more intriguing, it could be a valid but extreme value. This outlier might represent a unique behavior or a significant economic finding in your dataset. Blindly removing such a data point could mean losing valuable insights. In these situations, you would keep the data, potentially using a technique like Windsorizing to reduce its disproportionate influence on your analysis. The key is to understand why the value is extreme before taking any action. We've covered a comprehensive journey into exploratory data analysis. To recap our key takeaways, the process begins by simply exploring your raw data to understand its fundamental characteristics. From there, it's crucial to check for extreme values and compare the mean with the trimmed mean to assess the influence of potential outliers. The next vital step is to formally test for normality, often using the Shapiro-Wilk test, which dictates whether parametric statistical methods are appropriate. Finally, always supplement your numerical checks with visual diagnostics, particularly box plots, to quickly identify distributions and anomalies. Remember, the golden rule is clean data equals robust models. As a final word of caution, never rush straight to complex analyses like regression. Take the